Boa tarde. Sejam bem-vindos ao último dia da Semana da Geologia.
Então, para quem não me conhece, meu nome é Júlia Mattioli, eu sou aluna da Geologia daqui da UFMG, membro da Minas Jr e do CPEGEL. Eu queria agradecer novamente a presença de vocês e do professor Haakon Fossen pela palestra. Agradecer também todas as palestras e os palestrantes que a gente teve. Só apresentar um pouquinho nossos patrocinadores, são a Datamine, a SBG, a CAST, a PRAE e o CNPq. E a gente tem o apoio da Geologia BR e do IGC UFMG. E a comissão é composta por membros da Minas Jr e do CPEGEL. Uma coisa, eu queria pedir a todo mundo que não se inscreveu ainda se inscrever no site, no formulário que tem lá para a gente enviar os certificados. A gente vai passar a lista, mas só quem tiver inscrito no site que vai receber o certificado. E também qualquer dúvida, qualquer coisa pode enviar lá para a gente, para algum slide, alguma coisa, alguma foto, a gente conversa lá pelo e-mail. Qualquer dúvida pode procurar alguém da comissão.
Além disso, os slides dessa apresentação vão ser disponibilizados mais tarde, então quem tiver interesse vai poder ter os slides dessa apresentação e de algumas outras também. Sobre o professor, o Sr. Haakon Fossen é um estruturalista internacionalmente reconhecido, graduado em Geologia na Universidade de Bergen, na Noruega, e especializado em Geologia Estrutural nas universidades de Bergen e Minnesota, nos Estados Unidos. Ele é atualmente professor dessa área desde 1997 na Universidade de Bergen e participa de linhas de pesquisa por todo o mundo, como os dobramentos caledonianos no norte da Europa e o sistema orogênico da Mantiqueira no Brasil. Publicou o livro de Geologia Estrutural, traduzido em 2 línguas a partir do inglês, e livro-texto de vários cursos de Geologia Estrutural. O Sr. Fossen também tem várias publicações de artigos científicos e orienta vários estudantes em seus projetos de pesquisa. Ele estará dando a palestra Shear Zones. Sejam muito bem-vindos. Please, Professor.
Obrigado. Since my Portuguese hasn't evolved so much since Wednesday, I will do this in English too. Thanks for introducing me. Today I'm going to talk about shear zones. And let's see, this first slide, it's an example of shear zones actually, since it's here from Buzios in Rio de Janeiro. This is Julio Almeida, very nice shear zone in the magmatic rocks there. Many beautiful examples of shear zones in Brazil, many important shear zones all over our planet. These are very important structures, and I'm happy to be able to talk a little bit about shear zones. We will talk about what shear zones actually are, what kind of information they contain, how we can extract some of that information to understand the history they have experienced, and what assumptions we have to make to do that, and how realistic are these assumptions. So first of all, some basic characteristics of shear zones. They are what we call strain localization features or structures. That means that the strain is localized into a zone. There could be strain outside of this zone too, or the surroundings could be underformed. But within this zone, there is an anomalously high strain. And this can occur in any tectonic regime. So by that, I mean the extensional regime. We can have, just like faults, we can have normal faults, we can have extensional shear zones. We can have shear zones forming in the strike slip regime and in the contractional regime. We can have shear zones forming basically at any crustal depth. Close to the surface, we call them faults. although some people use the term brittle shear zones about faults, I guess they are mostly called faults near in the upper crust. And then we get through what's called the brittle plastic transition, brittle ductile transition, and we get the real, what people think about as the real shear zones, ductile, plastic, and they change characteristic a bit as they get down into the hot lower part of the crust and maybe even into the mantle, lithospheric mantle. They also occur on a large range of scales. The picture to the left is from a thin section from actually a sandstone, where you can see this dark layer being offset by the shear zone. And the picture to the right shows the Great Slave Shear Zone in Canada, the Canadian Shield, where this red marker is displaced in a dextral sense, very similar to what we see on the left. In the case to the left, there is about 1 centimeter of offset. In the case to the right, this scale bar here is 100 kilometers. So we are talking about like 500 kilometers of offset. Very different scales, very similar expressions. An example of a really big shear zone strain localization feature is the Trans-Brasiliano lineament, which you all know probably better than me. That, oops, I did that last time too. That runs across, or diagonally across, much of South America, and also into the African side, as far as I understand, into Sahara. Very, very long and impressive lineament that we can call a shear zone. It probably cuts across the entire crust. So there is some evidence that shear zones can actually grow into the mantle or extend into the mantle. Certainly through the astenospheric mantle. This illustration from Titus et al. Illustrates very conceptually and simple what people can read out of shear wave splitting data, geophysical data, based on the anisotropy of the mantle. So this is the green layer here, is the lithospheric mantle. This is the North American plate, California. We have faults in the upper plate, San Andreas fault system. And then the faults extend downwards and probably through the mantle, the lithospheric mantle. Then there is some evidence for a different anisotropy in the astenospheric mantle. So there seems to be shear zones that cut through the entire lithosphere. And if we go to, if we read papers from Brazil by people like Assumpção, 2006, who have done some very interesting work on shear wave splitting. There is the case of the Ribeira belt, where an anisotropy in the mantle shows up parallel to the belt, and this belt, as you know, is strongly influenced by strike slip. It's a big strike slip dominated part of the orogenic belt of eastern Brazil. Again, this anisotropy indicates that maybe this shear zone system at the surface extends downwards. I should comment that these arrows here are kind of the opposite sense of shear from what we have in the Ribeira belt. Just to make that clear, this is from a different paper. But it probably looks something like this. Here is a kind of a very quick sketch figure from the Ibero Belt, showing, that this shear zone may extend through the Moho into the asthenosphere. Go on the surface to look at these rocks. They are very, very, very myelonitic in the shear zone. So an example of a large, high-strain shear zone system. Okay, back to a little bit smaller shear zones. Actually, back to the beginning. How do shear zones initiate? How do they start? When I was a student, I was thinking of a completely homogeneous rock and seeing this little shear zone starting at the point and just growing, becoming bigger and bigger and bigger. But one thing is there such a thing as a completely homogeneous rock? Probably not. There's always some flaw, some weak part of the rock, or maybe more serious heterogeneities that can allow the shear zone to nucleate. This is a granite from the Alps that has developed shear zones. If we look at different shear zones, we oftentimes find evidence that they nucleate on this one, for example. This was probably a vein before the shearing started. It localized the shear deformation because it was probably weaker than the rock around. And then we have deformation also in the side walls here. So we can easily see the sense of shear. In here, the strain is much higher. Another example, which is quite interesting, this is from rocks that were brought down to maybe 50 kilometers depth in the subduction system. There is a fracture subhorizontal in this picture, and around this fracture there is a zone that extends from here to there. It shows up with a different color. That stuff is eclogite. So this tells us that this fracture probably formed at 50 kilometers depth, and fluids entered these dry granulitic rocks at that depth and infiltrated the granulitic rocks and transformed the mineralogy from something dry to something more wet. And that was the start of a shear zone. And when you look at these different shear zones in that area, they start many times as fractures and develop into ductile shear zones, and the fractures kind of become overprinted and less obvious. Shear zones forming from fractures. This example is also taken from a paper cited below here. Shows how shear zones can nucleate along the margins of dikes. This is a aplytic or granitic dike in a more coarse-grained magmatic rock. And this contrast in rheology between these two rocks is what the shear zone discovers and nucleates along. Very nice shear zone along the margin of the dike. And something that is very relevant for many parts of Brazil, this part of, or the part of Brazil that is east of here, particularly the Araçuí belt and many other places, is partial melting, and the way that shear zones can nucleate along melt in a rock that is undergoing partial melting. So I want to go back to this thing about shear zones, that they occur on many scales, but they also look to some extent similar on many different scales. This is Claudio Valeriano's car, professor at UERJ, Rio. He puts this car many places just for fun. It's a matchbox car, so it's only this big. Just to play with this fact that if you don't have a scale, it's oftentimes difficult to tell the size of the structure that you see on the picture. Okay, this is from a field trip in Norway last summer. And back to these two pictures that I showed before, from what you can see under the microscope, in this case, to the left, and what you can see on a large-scale map from the Canadian Shield, they look very similar. If we look, for example, there's something, people talk about self-similarity, and some still talk about fractal relationships, properties. At least there are some things that you can scale up and down, and that makes sense. And one of those things seem to be, for example, the relationship between the thickness of the shear zone and the offset. If you remove the scale bars from these two pictures, they look very similar in terms of offset versus thickness of the shear zone. It's just an approximate, just to illustrate this. And we can try to check this by measuring different shear zones, by measuring their offset or displacement versus their thickness. It's always a little bit subjective, but we can try to do that. I did that with a number of shear zones. I'll try to find some more in the future. This is a plot, thickness plotted along the horizontal axis, thickness of the shear zone, and the displacement along the vertical axis. And it's a logarithmic diagram. This is quite common to use for these kind of exercises, which means that it spans a lot of large range of thicknesses. This will be 1 meter, 10 centimeters, 1 centimeter, up to 100 kilometers thickness and displacement here. So we can clearly see that there is a, okay, so I don't have data from this range yet, I haven't plotted that. I have to find some examples. But there seems to be a correlation between the two, which looks quite systematic. It means that thin shear zones have small displacements, thick shear zones have larger displacements. And you can give a certain range here based on the uncertainties. So as the shear zones grow in terms of displacement, they also grow in thickness. Okay. Almost linear. People have been thinking about this, and it's not easy, the way that shear zones grow. Wynne Means, American geologist, I guess he's retired, he made this classification. Type of 1, okay, so what are we looking at here? We're looking at two stages, an early stage where you develop the shear zone, and then the shear zone expands, becomes thicker, but the central part becomes inactive. It basically grows outwards, leaving behind a central part that is then inactive. So you will get a kind of, this would be a cross section across that shear zone. This is gamma here, it's shear strain. So it grows and then it kind of forms a plateau and it just expands laterally. It never gets, the strain never gets higher than this kind of value here. That's something that you would expect, sorry, something that you would expect where you have what's called strain hardening. Strain hardening means that it gets more and more difficult to keep the deformation going. so it's easier for the shear zone to develop into the wall rocks, or the walls. Okay. Here's another type. Type 2 is what he called that. This shear zone is always active in the middle. And you create kind of displacement profiles like this one, where you have an early one like this, and the peak just gets higher and higher, and you get very high shear strains in the middle of the zone. That's something you would expect where you have strong strain softening or work softening. And there could be several reasons for that. There could be new minerals forming in the shear zone, maybe micas, platy minerals, that makes deformation go more easily in the middle of the shear zone. It could be an effect of recrystallization that makes the rock softer. It could be shear heating and things like that. So it would create a profile very much like this, high peak, not so wide. There's a type 3 where the shear zone maintains its thickness after a while. So we just grow, and it's also homogeneous. We'll just grow and grow like this. And maybe this is what we usually intuitively think of as a shear zone growth, where we have a shear zone that is expanding just like the first one, but the whole zone is active all the time. The central part has been active longer than the margins, so the strain is higher in the central part. So then you get a displacement profile where that looks similar at any given time. It just grows in all directions in terms of shear strain and in terms of width continuously. And then we can have all kinds of combinations of these. It's very difficult actually to know exactly how a shear zone grows. It can be active in one part at some time, and then it can jump to another part, or it can be active everywhere at the same time. It's not easy to tell. So this is a challenge. And that's probably why people haven't worked so much with this for a while, as far as I know. The other thing, so we talked about thickness versus displacement. We could also look at the length of shear zones versus displacement. And I've used some data from a paper, Pennacchioni, Journal of Structural Geology 2005, to illustrate this. There is not much data on this. We need more data on these things. But these curves are displacement data measured from, each of these curves represents one shear zone. And if you follow the curve from one end, this is one side of the shear zone, that's the other side of the shear zone, across the shear zone, and this is how displacement, this is one end of the shear zone, and this is the other end of the shear zone, and this is how displacement varies from one tip to the other. And we see that the shear zones have maximum displacement in the middle, more or less, just like faults. Of course, the displacement has to be zero at each end, at each tip. And then it increases toward the center, and then it goes down again toward the other tip. This is exactly what faults do, how faults distribute displacement, individual faults. So you can plot this data, and again there is a clear, nice relationship between the length and the displacement. So the longer the shear zone in map view, the higher the maximum displacement. This is the maximum displacement, these values in the middle that have been plotted. This is data from brittle faults. Many large range of lengths, large range of displacements, and they form quite a nice trend in this plot. If we plot the few shear zone data that I've found in the literature, we find that they plot more or less in the same kind of system here, the same trend. Maybe a little steeper. Again, we need more data on this for larger and smaller shear zones to see what this looks like compared to faults. But it seems like we are looking at very similar geometric relationships as those that we have for faults, which is nice. Another thing about faults that I talked a little bit about on Wednesday is that they grow not from one point to become bigger and bigger and bigger and bigger, longer and longer. They do that to some extent, but it's very important to realize that they grow in length by what's called linkage. So two segments connecting, and once they connect, they form a much longer fault. Maybe you remember this experiment that I showed. These are three different stages. Small individual faults scattered along a zone here, and they connect and form a continuous fault. And this is a map of shear zones, the kind of shear zones that I showed from in the beginning, a small shear zone. And let's see, so this is a map. We have some markers in blue, applitic dikes, I think. And the shear zones are running horizontally across this picture. Let's zoom in a little bit. This is from the same paper that I referred to. We can see the individual shear zones here in map view. And we can see that they seem to start to interact, to link up as they get close to each other. This one here, there is an example up here. Let's zoom in a little bit more so we can see better some of these examples. These two shear zones, they propagated and overlapped, and now they are about to, they probably already did link up. There's a connection between the two, and then if deformation proceeds, they are going to form a nice continuous shear zone. Not completely planar, but one shear zone. These two will probably link up. These two segments here, or maybe three, have already linked up. And some of these small jogs or non-planarities, like this one and this, probably represent earlier linkage between smaller segments. So maps like this are very useful. Again, fieldwork is important. And it tells us that shear zones grow at least partly by linkage, by connecting and forming longer shear zones by doing that. And when they link up, many over time, they can form large and fairly complex shear zone systems. This is an example, the state of Sao Paulo and Paraná here, right on the borderline. This is where this map is from, by Faleiros. And we can see shear zones. They are not straight, they are not planar, they are curved. And now that we know a little bit about how they grow in length by linkage, we can imagine that this zone of shear zones probably was individual shear zones at an earlier point that propagated and linked up, and maybe that's why we have this geometry which is not exactly planar. It's irregular. It's very typical. Let me go back. The next map is from here to show another thing that is a kind of scale independent. This rotation that we all know of pre-existing layering or foliation into the shear zone, that's telling us something about the sense of movement, sense of shear. As I said, many beautiful examples of shear zones in Brazil, and the Northeast is indeed a very beautiful one. Network of shear zones. And coming back to this thing about scale independence, the upper drawing is from a shear zone network in right at the border between Spain and France, Cap de Cruz, where we have very nice shear zone networks. And if you look at this drawing, and look, the scale bar is 2 meters. It's very similar to what we see in the Patos area, for example, where we have these curved shear zones connecting. Okay, so this tells us something about the processes forming these shear zones. So the way that they grow is kind of scale independent. It happens all the time, over and over again, as the shear zones and the shear zone system gets bigger and bigger. Just a few examples of shear zones, large scale, where we can probably see shear zones in different tectonic regimes. If we want to see really large scale things, seismic data is a good source of information. So what is this? This is a long, deep seismic line across a rift, the North Sea rift. And it's in time, 10 seconds is relatively deep. The moho is down here somewhere. We have the lower crust there on the mantle. And if we look at the lower crust, there is more reflections from that part of the crust than higher up. Let's put in some interpretation. These are sedimentary rocks and sediments in the rift and post-rift. These are faults that have been mapped from seismic data. And this is kind of an interpretation of the pattern in the lower crust. I mean, we can see lower crustal rocks at the surface several places, but it's interesting to look at seismic lines to see what's in the lower crust today, and we see this pattern. And many people think that these are patterns of shear zone networks. A little bit, maybe like this. Let's see. And then you have on seismic data too, sometimes you can see things continuing through the crust and into the mantle. And this may be an example of that. Let me see, put in the yellow line. So again, a connection between brittle fault in the rift that extends through the lower crust and into the mantle. And then maybe a shear zone network in the lower crust. Nobody has been there, we don't know for sure, but that's what many people think may be the case here. So this is important for understanding, in this case, the rift, the North Sea rift, geometry, thermal history, just to show that shear zones can be also economically important, at least indirectly. Another example of seismic data from Scandinavia, this too, of something that may look like shear zone networks. This is the thrust, Caledonian thrust. We talked about thrusts 2 days ago, with thrust maps above. And most of this stuff here is probably basement. So again, people are discussing whether these reflections here represent a shear zone network in the basement. It may look like that. Alternatively, they could be dikes that have been rotated. So again, we are not sure. I think in the future, seismic data and similar remote sensing data will be more and more important in understanding shear zones and mapping shear zones in the crust and the lithosphere. And this is, back to this is a prime example of shear zone networks in the strike slip regime. We don't need seismic data here because erosion has done the job and we can see things at the surface. Okay. Shear zones are also, they show different degrees of ductility. Some people talk about brittle and ductile shear zones. So what does that mean, brittle and ductile, really? And sometimes people confuse ductile and plastic. Ductile basically means that layers that were continuous before deformation, like this brown layer here, are still continuous after the deformation. Okay. Brittle means, in this sense, means that continuous layers were broken up to become discontinuous during the shearing. It doesn't really tell you that anything about the deformation mechanisms. You can have ductile shear zones forming in loose sediments with no crystal plastic deformation at all. It's a ductile shear zone. Some deformation bands, for example. Some pictures. Brittle ductile is just observation. You can see two discontinuities here, planes. And in between the layering is rotated. So there is a ductile component here and a brittle component there. So that would be a brittle ductile shear zone. Most people would call it a fault, probably. The example to the right, we have layering in the quartzite. And you can see that this layering is almost continuous, but not quite. It's broken up a little bit by these fractures. So again, we have a mixture of ductile and brittle deformation. And back to this, it's a different diagram. Depth, kilometers down to the lower crust. And temperature in parallel with depth. Actually, temperature is more important than depth. The upper part faults, and then you get, you can have ductile deformation at the surface, but plastic deformation you can only get once the minerals that your rock consists of start to deform in a crystal plastic way. And there is two levels in the crust that are usually very important. In the continental crust, that would be where quartz starts to behave in a plastic manner, which is approximately around 300 degrees. And the other is where feldspar starts to behave in a plastic manner. Maybe 450 degrees, approximately. Those are two very important levels in the crust. If your rock has a lot of quartz, then this would be the most important transition from brittle to plastic deformation. But in some cases, there is a lot of feldspar, and this becomes important. And this is just an illustration of the network that we usually, or many times, find in the high temperature part of this system. Here's some pictures just to illustrate brittle deformation in the upper crust. And it's not so easy to see, but there's brittle deformation, fracturing, rotation, frictional sliding of grains in this zone. And then you start below 300 degrees to see quartz behaving in a plastic manner. I don't know if you can see this picture in the middle, but there is feldspar in here that has fractures, like small slip surfaces. Feldspar is behaving brittly, and the quartz around is behaving in a plastic manner. So if there's a lot of quartz, then quartz is going to control the deformation, and feldspar is going to be breaking in between the quartz. Also put in a thin section to the left here that I got from Carolina Cavalcanch, showing the typical ribbon structures that you can find many places in for example, the Alsoe belt, in Hibera belt, I mean, where the temperature was very high. So all of these different depths, the shear zones at different temperatures, have their specific characteristic expressions, not only at the macro scale, but also at the micro scale. And we talked about this classification of mylonites and the way that was only understood in the late 70s. So it's not a very old part of the structural geology science, this thing about understanding shear zones and fault rocks. Okay, that's the first part. Get some water. In the next part, we'll look at simple shear zones. What they can tell us, and how we can extract information from shear zones that are simple shear. Simple shear zones. Again, this was mainly in a systematic way born out of John Ramsey's work. There's a paper by Ramsey and Graham from 1970, I think, yes, where they describe kind of very clearly what a simple shear zone is. So we have a shear zone with raw rocks on each side, and the shear zone develops something like this. If there is no fabric in the rock to start with, we get a new fabric that develops during shearing, and this fabric rotates as shearing proceeds, and this rotation is related to strain. we call these strain trajectories when we can draw lines based on the new foliation that kind of traces the foliation through the shear zone. And that's what he did in his paper. Let's see, it's important to understand these things. So we have a couple of different parameters during simple shear, and one is shear strain, which has to do with how much you shear. For example, if you have a box like this and you shear it, then the change in angle of this vertical side of the box, the new angle, is going, the tangent to that is going to be the shear strain. So the more we shear this box, the higher the shear strain. That's what's plotted along this graph. The other thing is this angle between the strain ellipse, the long axis of the strain ellipse, and the shear zone. And that angle is going to decrease during shearing. And the relationship between these two is shown in this diagram. This ellipse at the top illustrates the strain, and the angle here between that ellipse and the shear zone is what's plotted along the vertical axis. Okay, let's do this. Here we have the strain ellipses marked on this theoretical shear zone. And it's very idealized, but you can see the strain is increasing from the margins into the center and out again. And as the strain increases, the foliation trajectory makes a lower and lower angle to the shear zone. So that's what this diagram means. This is what the ellipse does in a different figure, rotates toward the shear plane as strain accumulates. Okay. To describe strain, we can use the ratio between the long axis and the short axis of the strain ellipse. Simple shear is a plane strain deformation. So we only have to look at this in 2 dimensions. The y-axis of the strain ellipsoid is not changing its length, so it's easy and simple. Simple shear should be simple. So here we have all these 3 parameters: the theta, the angle that is the angle between the x-axis of the strain ellipse and the shear zone. Shear strain increasing to the right along the horizontal axis. The blue curve indicates that relationship. And then we have plotted the strain ratio x over z, increasing upwards. So it starts out at 0. 0 at the beginning, there is no strain. X divided by z is down here in the corner. 0, and then it increases more and more as strain accumulates. Okay, let's see. So during this strain accumulation, the rock experiences changes, of course, and in terms of fabric, you may go from something like this outside of the shear zone to something like this once you get into the shear zone. And we move to the right here, higher and higher shear strain. The objects that were fairly spherical to start with are now becoming long ellipses, and we move a little bit more into the shear zone, and it becomes difficult to actually to identify these objects at some point. Very high strain. So this is the R ratio, would be the long axis divided by the short axis, will increase as the shear strain accumulates. And eventually we'll get some rocks like this where it's impossible to identify the original object of that rock. Or in other cases we get transposition, small folds floating around. Very difficult to reconstruct what this rock was originally. If you want to play with these values, there is a spreadsheet on my website and my book's website where you can put in different shear strain values. There's a range here. You get the R value calculated, and you get this angle theta prime calculated. You can plot these things. Okay, so using these relationships, we can extract some information from shear zones. If we make a traverse, a cross section from one side to the other, from A to B, we can use the orientation of the foliation, for example, to calculate shear strain at different points. And we can graph that like this. There's A is here and B is over to the right. So we get shear strain increasing toward the middle and then decreasing again. So why would we do that? Because based on that, we can calculate the displacement or offset of the shear zone. Here's an example of a shear zone, a small shear zone, where we have traced the foliation across this shear zone in two places. And this is the interpretation of the foliation. Okay, so we can take those observations and plot shear strain. So shear strain along the horizontal axis, and this will be from the top to the bottom. And then we get these curves. So if we sum up kind of or integrate the shear strain over this distance, we can actually find displacement. The simplest way to do that is just to calculate the area below these graphs, which we may have done as an exercise already. So if you just count, the squares here approximately. In this case, so this is the curve to the left is this transect, and the other one is this transect. You end up with something approximately 8 centimeters of offset for the first transect, 8.4 centimeters approximately for the second. So very similar, right? So we know it's very difficult to see the offset of this shear zone, the displacement, but you can calculate it and get an estimate, assuming this is simple shear. So that's useful. Okay, I'll skip that. So if we think in time as a shear zone evolves, maybe something like this. This curve would grow like that, depending on how the shear zone evolves. So we can estimate displacement even without markers. If we have markers, that's better. Then we can double check and see if the assumptions hold that we make. So that's just what we were looking at now was the foliation that forms during shearing. We can also look at pre-existing structures that cross the shear zone. It could be layering, for example, or a pre-existing foliation. For example, here we have put in a marker that is perpendicular to the shear zone that gets rotated during shearing into the shear zone and offset. And it comes back to its original orientation on the other side. We can have any orientation. We can have, for example, a marker like this would have a different geometry in the shear zone. So there is this nice relationship between the orientation of the marker outside of the shear zone, the angle between that marker and the shear zone, beta 1, beta 2, for these two cases, that you can use, and then the local angle within the shear zone. The relationship between those two, beta is the angle here outside of the shear zone, and this angle will be the local angle to the shear zone within the shear zone. So you can calculate gamma from pre-existing markers too. And of course it depends on the initial orientation of those markers. You can make these graphs if you want, showing the initial orientation and then how they change orientation depending on gamma, the shear strain. And then you can calculate the same kind of graphs that we just looked at here for the other case, just by using pre-existing foliation. Like this foliation, for example, from Santa Cruz in Spain. This is a pre-existing foliation. It rotates into the shear zone. You can measure how this foliation changes its orientation at different places, calculate a shear strain profile across the shear zone, and find the offset. Very basic but useful things to do. So that's what was kind of explained in very clear terms in the 70s. In the 80s, kinematics was the next big thing. That is very important. Kinematics, sense of shear. So the idea then, people were still thinking mainly in plane strain, was to study the section parallel to the lineation and perpendicular to the foliation, and check the asymmetry of structures that you can find in those sections. Because we now know how the lineation develops during simple shear. This illustration kind of shows what's going on with the strain ellipsoid during simple shear. And the shadow is kind of the projection of that lineation onto the shear plane. So if we look at the shear zone from above, look down at the lineation, then that lineation would point in the direction of shear. So that's why we're looking in the section parallel to the lineation, perpendicular to the foliation. And it's all about asymmetry. We're looking for asymmetric structures, and preferentially as many as possible, to determine the sense of shear. And this has to do with flow. During simple shear, the one to the left here in the middle, particles move in the horizontal direction, that means parallel to the shear zone, and only in that direction. The displacement field would be something like this. That's what the particles do. They don't move across these lines, only parallel to these arrows. For pure shear, which is shown at the bottom left, the pattern is completely different. It's symmetric. So much more symmetric, and it gives more symmetric structures. That's important. We'll come back to that. So SC structures, the way that magmatic rocks in particular develop C surfaces, small shear surfaces that initially tend to be parallel to the shear zone, and then new sets that may be inclined to the shear zone, oblique to the shear zone walls, are typical SC structures, asymmetric, and can be used to find sense of shear. So C and then C prime, if you are able to distinguish between those two. So C surfaces and C prime. Sometimes, oftentimes you can't distinguish between those two, so you just call them C surfaces. The other ones S for the foliation. Okay. An example, deformed granite. This is where these structures were originally described in northwestern France, Armorican shear zone, I think. And here's the S. C more or less horizontal, and then you get the C prime cutting down like that. These are very common structures. This is from Rio, Ipanema. If you go there, you can look at these nice structures. Shear bands, C surfaces that rotate from S and into these, the S foliation rotating into the C surfaces. C tend to be much longer and more continuous than the S. The S is rotating in and out. Beautiful asymmetric structures. Sometimes you can even pick them out like this. Very nice example where you have micas. So when you see rocks like this, you can measure different things. You can measure S and you can measure C, but you can also, if you have a little bit of 3D kind of geometry or outcrop exposure, you can also measure the crenulation axis. That's this axis extending into the picture. So if you look at this as a fold, it would be like the fold axis. And that direction would be at a high angle to the slip direction or shear direction. It's a useful thing to measure. Here's an example from the Lancina shear zone, farther south along the Ibero belt, with, let's see, S moving out of and into these C bands. The blue lines here are C surfaces. And then, so there is two sets of structures S oblique to these C structures. Very important structures to map in the field. Can sometimes be a little bit difficult to distinguish from cleavages. So you have to be aware of that. That's the S. Okay. What we oftentimes are looking at, if this is simple shear, we can still have simple shear and rotate the layering back like this, the S, and form C structures. Because these two operations, these two deformations, rotation and shear along these shear bands, the C surfaces, kind of sum up to simple shear. Sometimes you can also have slip along the S surfaces, so you have three different components. So in a simple shear zone, these two or three kind of modes of deformation on the local scale have to add up to simple shear. Strain partitioning, you partition it into rotation and localized shear. So you can say that the C surfaces are kind of small shear zones within the bigger shear zone. It's another way of looking at that. We can skip that. There's many criteria besides of SC structures per se. There is where you have dynamic recrystallization, crystals recrystallizing all the time during deformation, you get kind of a finite foliation, finite strain foliation as myelonitic foliation like this. And then you can see internally an oblique foliation defined by less strained grains that recrystallize. They get a little bit strained, but then they recrystallize again, and then they get a little bit strained, so they form an oblique fabric. And mica fish are common. CPO patterns can be asymmetric with respect to the foliation. And many other things. Porphyroclasts, porphyroclasts. Different kinds of those are put in. Let me see some examples here of a delta type to the left here. So this lower animation shows how that develops by the feldspar recrystallizing into these tails, and this tells you the sense of shear. So that was sigma, sorry. So this is the delta type. The delta type is similar, but it has more rotation, so that these tails kind of cross the central line here from one side to the other, like that, and very long tails sometimes. This kind to the right is symmetric, so it's not very helpful, and it may actually indicate a more coaxial type of deformation than simple shear. Then there's these quarter structures, is what they are called in the textbook by Pache and Throve. And those are also important to understand. If you have for example, a rigid object and shear like this, then you get shortening here. So thinning in this quarter, and same thing at the lower left side. But on the other side of this object, you get material accumulating and folding, just like what we see here. Also very good kinematic indicators. I showed this sample on Wednesday, I guess. This is a field sketch of an example of this situation. There's also myrmecites forming in the opposite quadrants sometimes if you have high temperature deformation. I also said that, you can get cleavage, a new cleavage or new foliation forming here. It doesn't mean that it's a different, separate phase of deformation. This is all progressive deformation that we are talking about. So I'll make that point again. Progressive deformation and the way that you get folds forming in shear zones, and you can form very complex fold geometries if you have competent layers in weaker rocks in shear zones during progressive simple shear. Okay. And I showed this illustration too, the way that you can have folding and refolding during progressive shearing. So that's all these things can form during simple shear. I'm going to make things a little bit more complicated, which means a little bit more realistic, and talk about subsimple shear. Subsimple means it's not as simple as simple shear. Of course, everything should be made as simple as possible, but not simpler. We need to make things a little bit more complicated if we want to capture the truth sometime. There are some things we can look for to check if our shear zone is simple shear or not. So if we have a marker that is displaced, we can use those. We can do those exercises that I showed using the foliation, new or pre-existing, to calculate offsets across the shear zone, and see if it matches the offset of this marker. If it doesn't, it's probably not simple shear. We can try to look for the initial orientation of the XY foliation of the strain ellipse. If that's significantly different from 45 degrees, it's not simple shear. We can look at the shear zone walls. If they are not parallel, if they are curved, it's not simple shear. And if there are structures indicating conflicting sense of shear, that's also a bad sign. Here's an example from a paper by Carol Simpson in 1993 of a shear zone that cannot be simple shear, at least not in this part. You can see the two margins are diverging to the right, not parallel, and not even straight. So it's not simple shear. She did this exercise to calculate displacement at various places, these 4 places, and it gave a little bit confusing results. Let me see. I forgot to put that on. But it gave different displacement at different points in a non-systematic way. 9 centimeters, 4 centimeters, 2.5 centimeters, and then back up to 5 centimeters. So here's also, within this shear zone system, this is not straight, nice, or planar shear zones. They're very nice, but they're not planar. So within this system, there is definitely many places where the deformation cannot be simple shear. So this is 3 different examples to the left of a kind of schematic shear zone. The foliation in a simple shear zone starts at 45 degrees to the shear zone, and then it rotates to become lower and back to 45. If we see that the foliation starts out with a higher angle or a lower angle, we have something else that is not simple shear. This is one thing that you can use if you find in the brittle ductile shear zone small veins. These veins always open perpendicular to the instantaneous stretching direction. The instantaneous stretching direction is the direction that is, any line in that orientation is stretching faster than any other line. In these shear zones with veins, the veins will rotate during simple shear, so you have to be aware of that. Then you have to look at the tips. The tips would always be the youngest part of the vein. As they rotate, the tips, it would always have this orientation perpendicular to the maximum stretching direction. And you can get a new set like that. Like this. Okay, let me see. So that's the maximum stretching direction. So we have let me see. So the maximum stretching direction is always the same it's very common to confuse the maximum stretching direction with the strain axis. The maximum stretching direction is always in the same direction. And then you stretch things and the things rotate, so the strain ellipse will rotate, but not this stretching direction. And this direction will always be at 45 degrees to the shear zone for simple shear. So you can use this to check whether you have simple shear or something else. If you find veins like this, check the tips. So we're going into a little bit more complicated stuff. Vorticity, subsimple shear. And you probably have to go through this several times if you haven't done so already, but there is pure shear and there is simple shear, and you probably know those. And then between those two there is a whole range, a spectrum of deformations that are called subsimple shear. This maximum stretching direction, like I said, for simple shear is at 45 degrees to the shear zone, always. For pure shear, it's parallel to, there is no shear zone, but it would be parallel to the shear zone if there was. For subsimple shear, it's somewhere in between. The flow pattern, we have to mention that too. For pure shear, it's symmetric. The particles just flow in a symmetric way about the two coordinate axes, called flow apophysis. For simple shear, they move in horizontal direction. For subsimple shear, it's more complicated. You have two lines here that separate particles that move in the shear direction and particles that kind of move in the opposite direction, move down and back against the shear direction. The more pure shear we have, the bigger this field will be, and the angle between these two apophyses is usually called alpha. A little bit complicated, but it's very important to understand how particles behave in a system, in a shear zone, whether it's simple shear or subsimple shear. You need to understand that to make any progress. So this has consequences for what structures do, how they form, what kind of structures form and their orientation during shearing. For simple shear, everything rotates in the same direction. So let's take this example. We have two markers, so we can see what happens to these markers, and a strain marker here and a circle that is going to be deformed. This little thing to the right here indicates the maximum stretching direction like this. And there's also a maximum shortening direction that is perpendicular to that. And there is two fields. This is not the strain ellipse. You can think about it as the incremental strain ellipse. But there's two fields. The white field, anything within that white field is going to be field stretching. Anything oriented within this colored field is going to experience shortening at any given moment during the formation. Let's see. So we start to shear this thing. This layer dipping to the right is in that colored field of this ellipse down in the corner. So that's going to be shortened. As long as it is within this colored field, it's going to be shortened. The red was just vertical, so it's moving into the white field, which is the field of instantaneous stretching. So it will be stretched. So we mark this by little boudins like that. Let's do another increment of deformation. One more. One more. Now we see this layer, this tan layer here is almost vertical within the shear zone. it's getting close to this boundary between the colored and the white field. Once it crosses that vertical line, it's going to start to experience stretching. And this happens now. So now it's being stretched again. Not again, but it's being stretched. The other one is always being stretched. So look at what we have. We have early folds that have been stretched. Because initially we have shortening of that layer, it rotates, and then it gets into the extensional field, the extensional sector, and gets stretched. So you can form boudinaged folds, but never folded boudinage structures for simple shear and subsimple shear. Okay, one more a little bit difficult, maybe complicated thing. These are the sector we have been talking about down here. The white field of extension and the black field of shortening, contraction. So with increasing strain, we get a new sector here, and that's the sector of lines that was initially in the shortening field, instantaneous shortening field, and that moved into the extension field. And that field is going to be larger and larger as structures rotate. So it's going to be larger and larger down with increasing strain. Okay. So that's simple shear. This is pure shear. It's all symmetric. Now look, this is now different. Let's go back. So it was like that for simple shear. Now it's like this. Shortening is vertical, extension is horizontal. And it's all symmetric. And, oops. And nice, let me see. So we get very symmetric pattern here. Subsimple shear is a combination of these two. And we get, if we look at this again to the right, we get this sector that we saw for simple shear, where lines or markers go from the contraction to the extension field, but we get a little bit, we don't get a symmetric situation, but we get a small field on the other side too. And those are lines or markers that rotate in the opposite direction. Has to do with this field here, where particles kind of move back against the shear direction. We can use that to estimate what's called the vorticity number. And the vorticity number is it's a number that tells you how much simple shear there is relative to pure shear. If you put a pedal wheel, this kind of thing, or look at a kind of spherical marker in a pure shear situation, this pedal wheel is not going to rotate because the flow is completely symmetric. The particles in this box will move some to the left, some to the right, and keep this steady. It will not rotate. In simple shear, all the particles are moving to the right above this wheel, all the particles are moving to the left below it, and it will rotate easily. For subsimple shear, it will rotate a bit because there are more particles moving to the right than to the left, but not as fast as for simple shear. How fast will it rotate? That depends on how much simple shear you have relative to the pure shear. It depends on what's called the kinematic vorticity number. So for simple shear, if you have a porphyroclast, porphyroblast, whatever, some object like this, it's always going to rotate in this direction. For pure shear, that should not be pure shear. That should be, sub-simple shear. So simple shear with a pure shear component. Then the long objects are going to rotate, most of them, toward the shear plane. If they have this orientation, they're going to rotate the opposite direction. And if this ratio between the short and long axis of these objects is long enough, they will get stuck in the horizontal orientation. So if they are long enough, they will get stuck parallel to the shear zone. How long do they have to be relative to their thickness? That depends on how much pure shear there is relative to simple shear. And this is that ratio between the long axis and the short axis. And this is the angle that you can measure in the field between the orientation of these objects relative to the shear zone. And then you'll find a critical value. If the aspect ratio is higher than that critical value, they will all be close to the shear plane. And this is a method. I know this is a little bit complicated to understand, just like that, but this is trying to explain a method that many people use to try to estimate vorticity, how much simple shear is there relative to the pure shear component. Let's skip that. Another way that people do that, you remember we looked at this marker that was first folded and then it got stretched. So you got stretched or extended folds. So it started out in this field and then you got this stretched extended folds. For sub-simple shear, you get these two fields like that, where markers can rotate, in this case to the right, but if they are close to this orientation, they can rotate to the left, opposite to the sense of shear. So if you have a lot of markers, could be veins, for example, dikes, and then you can measure their orientation to see if they show evidence of stretching only, or if there was folding or shortening before the stretching. And then you can plot their orientations and try to define these fields. And then if you can extract strain from the same rock, so we need a lot of information, then you can say something about this vorticity number. Then you can say something about how much simple shear there was relative to pure shear. It's complicated, but people have made these observations and tried to estimate vorticity, kinematic vorticity. How common is it? I mean, we have lots of shear zones. Are most of them simple shear, or do they have a component of pure shear, and how much pure shear, if so? And I went through the literature and I plotted the different estimates that people have made so far, and I think I got a lot of the current literature covered. And the simple shear is to the right of this graph, pure shear is to the left, and this is the spectra in between. WK, kinematic vorticity number, should be 1 for simple shear. So there is some simple shear, but the majority of shear zones that have been explored seem to have a kinematic vorticity number around 0.6 to 0.8. That means that they are simple shear with some pure shear. Most of the shear zones have a component of pure shear. There is a complicating factor in this, which is compaction. So in most of these shear zones, they think that the shear zones do not experience compaction, because I don't want to go into that, but that's can add some complications. We assume constant volume. So that's interesting. So we have to take this into consideration and try to extract this information if possible, if we are studying shear zones. It gets a little bit complicated. It was easier in the 70s when we only had simple shear. Let's make it let's look a little bit more at this. This is some considerations we did in a paper from 1997. Say if you have a shear zone, horizontal shear zone, and when we use this box with a circle in the middle to illustrate what happens during a deformation, we want to move the shear zone 2 units, 2 times its thickness, if you like. So we want to create a displacement 1, 2, from 1 to 3. So move this point 2 units in the horizontal direction. It could be 2 kilometers, it could be 2 centimeters. It doesn't matter, this is just a theoretical case. If we do this by simple shear, move this point 2 units to the right, then we create this strain ellipse. If we do the same with pure shear, we move this corner 2 units to the right. Pure shear also involves some shortening across the shear zone, so it moves a little bit down too. Then we get another ellipse, and this ellipse is more elliptic than the one we get for simple shear. So there is more strain involved in pure shear than simple shear in this case. Then if we do sub-simple shear, we can do the same 2 units with less strain than pure shear and less strain than simple shear. This means it's more strain efficient. There is less work involved if you combine pure shear and simple shear. I think you can see that from this simple example. Sub-simple shear, you can move things more efficiently with less work, less strain. So it looks like a more clever way of deforming a rock. Exactly what kind of sub-simple shear you should use to minimize strain actually depends on how much you want to move one wall relative to the other. And the offset, so that's the offset, the WK would depend on the offset. One of the challenges with involving pure shear in shear zones is that if you have pure shear, this is pure shear down here, the material is squeezed out on each side, or on one side, depending on how you put your coordinate origin. For simple shear, there is no such squeezing out of material. But this can absolutely be possible if the shear zone changes its thickness. You can make more space in some places so material can flow. On a large scale, it's what people think happens where they talk about channel flow, for example in the Himalayan origin, where there is a lot of melting going on and things can flow to the surface. So the surface would be, it's a free surface, so material can be eroded. And there's also a climatic part of this, that there's if there's a lot of rain along the mountain range here, that will help erode these units. So this is a large-scale example where sub-simple shear seems to make sense. Okay. In other origins, there's especially in hot origins, there is some indications that shear zones are actually three-dimensional. You have to look at in 3 dimensions because subsimple shear is still 2 dimensions, and that's what's going to talk about in the next parts. Is strain in 3 dimensions. This is getting more and more complicated, but that's how it is. 3D strain, okay, especially where you have populations or systems of shear zones. Things very easily get 3-dimensional. This is from a paper by Chardon and others in 2009, and they define ultra-hot origins, and they have this very nice illustration of shear zones, and you can see from this illustration, when you look at these different sections, that things are moving in definitely more than one direction. So we have 3-dimensional strain. So there is a plane strain, just to remind you, where everything is going on in one plane in terms of strain, and there's shortening in one direction, extension in the other direction, and the third direction is constant. Then there is uniform extension, uniform flattening as 2 end members of 3-dimensional strain, and everything in between that you can think about. And we looked at the Flynn diagram the other day, where you can plot these geometries, both simple shear, pure shear, and any subsimple shear will plot along this line. So that's one thing that you, if you can, please try to find the strain geometry, try to find objects that you can use to measure strain, to find out if you have plane strain, or to find out if you have more flattened objects or more stretched cigar-like objects. Because if you do, you are not dealing with simple shear, you're not dealing with pure shear, you're not dealing with subsimple shear, you're dealing with something more complicated. In terms of, we talked about L tectonites and S tectonites and LS tectonites on Wednesday. And you can do the same thing with shear zone systems and look at how these systems, the geometry in 3 dimensions, and maybe that can also be used to say something about the overall strain. This is a kind of a flattening situation here at the top. In the middle, maybe more like a plane strain situation. And the lower diagram here is from Krukenberg and others, 2010. You have more something similar to a constrictional fabric, but at a much larger scale. So 3-dimensional expressions of 3-dimensional strain. Let me see, why did I put this one in? I think it was just to remind you that these kind of patterns are typical for hot, lower crustal, middle crustal situations. And people have started to think about what happens when you have these networks of shear zones. They're not parallel, so it's 3-dimensional strain. This is an illustration made by one of my former advisors, Peter Huddleston, where you can see a very simple shear zone network. In this simple shear zone network, there has to be different types of deformation going on in different elements of this network. And he pointed out that there's constriction in some parts, maybe simple shear or plane strain at least in other parts, and P flattening going on in other parts of this network. This is something that will be very interesting to model numerically, to see how things would vary in a network like this. So if you go in and look at shear zones, an outcrop here, an outcrop there, they would look very different, but they will be the same system of shear zones. So things are not so easy. This change or jump to 3D, which happened in the 80s and 90s, actually the simplest and most popular model was this one that was presented by Sanderson and Marchini in 1984. They made two rigid objects, two walls, rigid walls, that kind of moved with a horizontal shear component and also shortening perpendicular to the shear zone that caused extension of this shear zone in the vertical direction, something called transgression. And this is okay, the deformation matrix for those of you who are interested, that I worked on in the 90s. So this is combining contraction, which would be pure shear, and strike slip or simple shear in a different way, so that you create 3D strain, or combining extension and strike slip simple shear to form transtension. And depending on how much simple shear and how much squeezing pure shear you have, you create different situations with different strains and even different strain orientations. I'm not going deep into this, but it's a very simple model, but the different possibilities and results are it's relatively complicated. If you have a lot of pure shear, you get a vertical lineation, for example. If you have a lot of simple shear, you get a horizontal lineation, long axis of the strain ellipsoid. And this long axis, the lineation, if you like, is never going to rotate into the shear plane. It's going to get stuck before it reaches that point. And things like that. And the strain paths in the Flynn diagram, as these things evolve, are very interesting and also a bit complicated. The last parts. Everything we have been talking about so far, which has already become a little bit complicated, is what's called steady state deformation. That's what most people assume. So what does steady state deformation means? It means that things are steady, not changing in terms of the situation, in terms of the stretching axis, the instantaneous stretching axis. They are fixed. The direction of maximum stretching at any given moment is always going to be the same during the deformation. So these fields are always going to be the same. That's for simple shear, right? So the conditions, if you like, during shearing, in terms of these parameters, it's always going to be the same. So this is always the same down in this corner here. And that means that what we call the kinematic vorticity number is also going to be constant. Okay. So if we want to find out that that's actually the case, we have to look at incremental strain markers, or things like dynamically recrystallizing grains that only record the last portion of deformation. So then we get an idea about the situation during the last part of the history. And then maybe look for some other indication for the earlier parts of the history. For example, parts of the shear zones that were left during the formation at an early stage and preserved. Remember this from not so long ago? We looked at how strain accumulates during different kinds of plane strain deformation, and we concluded that combination of pure and simple shear is most strain efficient. You can do make a displacement with less strain if you use subsimple shear. And you have to use, if we allow for non-steady deformation, we can let the relative proportion of simple shear and pure shear change during shear and deformation. So for example, in the beginning we can have more simple shear, and then later we can have more and more pure shear. That would be an example of non-steady deformation. And if we allow for that, we can simulate what happens. And what happens is, and this is published in that paper from 1997, is that so WK1 at the top means simple shear, WK0 down here means pure shear. So it starts out the non-steady state curve with a lot of simple shear, high simple shear component, and then to proceed with a minimum strain kind of effort, you reduce the kinematic vorticity numbers, so you add more and more pure shear to end up with a minimum of strain. So we produced an offset of 2, and there would be, you would end up with a kinematic vorticity at the end of that deformation of 0.65. If you go all the way to 6, offset of 6, the last part of deformation will be very pure shear influenced. WK to 0.25 or something like that. Now this is just very simple considerations, but it tells us that we are probably oversimplifying things when we look at shear zones. So in the end here I will point out a few things. I guess it's very easy, or actually I think many students struggle with even simple shear the first time they are exposed to simple shear, to look at how the strain ellipse forms and rotates, and foliation rotating and all these kind of things. But really shear zones are much more complicated than that. But it's good to have these reference deformations: simple shear, pure shear, plane strain, transpression, transtension, to relate to. It's always like that. Simplifications are always necessary. The nature is too complex to describe in all its details. We can never understand the development of shear zones completely. So we have to make simplifications. So yes, we can start assuming simple shear and see where that takes us, or subsimple shear. The truth is probably a little bit more complicated, but we need to try, and maybe the deviation from these models is not so great that it will affect the goals that we are trying to achieve. But we need to understand the limitations of the assumptions that we make. I think future exploration of shear zones will rely a lot on numerical modeling together with field observations, going back and forth between models and field observations. I think that's a way that we need to move in this field. Shear zones, so in case I scared you too much, shear zones are extremely important, extremely interesting and intriguing structures, well worth to study, from the micro scale to the scale of plate tectonics. So allow yourself to get fascinated by shear zones. It's worth it. So that's the end. So thank you for being patient.
Thank you very much, professor. Alguém tem alguma pergunta? Antes disso, alguém está com a lista de presença? Só um recadinho, gente, a nossa próxima palestra com o professor Daniel Galvão, ela foi mudada de lugar, agora ela vai ser aqui no auditório, tá? Logo em seguida. Não vão embora.
Hello. First of all, thank you for the excellent presentation. My question is about the displacement calculation. The beginning, you talk about it. The main examples, the most examples you gave, is about one rock and the deformation of the minerals inside of it. But thinking in a gold company reality, when you have a wide shear zone and two different rocks inside of it with different deformations, should we use the geometry of these rocks to measure the angles and extrapolate it from the mineral deformation, or should we go, like we have on one rock with the host rock with the mineralization and like a mineral formation and a schist? Should we get the geometry of these rocks to measure the angles and then calculate the displacement? Because it will help a lot to find new targets for the company, for the exploration. Or should we go to the rock and calculate the angles in the minerals, the deformated minerals? No, I don't know if you understand my question.
I think, well, geometry is what we have to use. I mean, that's what we can observe in the field. Then the problem is usually to understand what the geometries mean. Some shear zones are very complicated depending on the amount of strain that they have seen. But yes, definitely anything geometry, I mean, you have to measure and try to understand how it formed. That's the only way that we can understand shear zones. I guess you wanted a more specific answer. To calculate displacement, I mean, you have to try to figure out the strain, the amount of strain in the zone somehow. And I showed a couple of simple examples of how to do that. If you have different lithologies and things soon get pretty complicated. I also showed a very rough relationship between shear zone thickness and displacement. So that gives you some clue, but there's a lot of variation and uncertainty, so it's not a very precise measure of displacement. But you can use these different things together and see if you can get closer to. And then there is in some cases difference in PT conditions on each side. Is this a what kind of a shear zone? It's a strike slip shear zone, or yeah. Okay, yeah. So it's difficult to say something more specific without knowing more.
You can't find the non-deformated rocks near the shear zone. It's very complicated to find it. In the reality, everything is very complex.
Yes, that's how it oftentimes is, unfortunately. It's not, but
in your presentation, you told us about 4 different types of shear zones. I would like to know what parameters, what should we look in the field in order to see which type of shear zones are we working on? I mean, what's the main parameters to look for in the field?
So different types of shear zones in terms of simple shear and sub-simple shear and 3D, or what? Yes, the way that shear zones evolve through time. Some shear zones are always active in the central part. They never get much wider. Some shear zones leave the central part, and they just, the deformation kind of migrates into the walls, and this is like I said, it's also difficult to know if it's a big shear zone. Of course, at someday we'll be able to date deformation in different parts of the shear zone, and some big shear zones we can do that already. Like maybe the big shear zones in the northeast, you could try to do that. I don't know. You can try to look at rheology if there is new growth of weaker minerals in parts of the shear zone. You can kind of assume that those parts were active during the last stages. So considerations like that, I think, and also, yeah, yes, it's difficult. And it's important to be creative. I mean, each case is special. In each case, you have somewhat different criteria, different things that you can use. So, but this is, yeah, it's a puzzle. Thank you. So I just, since this is my second and last presentation, I just want to say that I'm very impressed by what you guys put together here. This week of geology is very impressive. So I thought I would like to give you a copy of my book that I think you have some kind of, the new edition, you have some kind of arrangement where students can share the book. So I only have one copy with me, but I hope you would make some. Because it's really impressive what you put together. Okay.
Isso vai ficar na biblioteca do CPEGEL, gente. Obrigada. E agora we also would like to present you with this mineral. There is this mineral only here in Brazil. It's Brazilianita. This is our little gift for you. Thank you very much, Professor. Thank you. So now you could pick a number so we can fazer o sorteio. De 1 até 121. Ciro, primeiro kit é seu. Glauber Fajardo. Foi embora? Another number, please. Fernanda Cristina Souza. Just one more. E o último kit vai para Pedro Henrique Pinto.
Gente, rapidinho. Queria agradecer a presença de todo mundo, lembrando que a palestra vai ser aqui. E antes de vocês irem embora, devolvam o radinho e depois vocês retornem para a palestra. A gente já vai começar, por favor. Ai, será que eu tô indo embora, gente? Será que eu tô indo embora? Eles vão comer. Pode. A gente vai começar a botar coisa. Não, peraí. Eu tô com medo de todo mundo ir embora.